Hello everyone. Today I will discuss a problem set from Mathematical Financial Economics, a basic introduction. Let's start. Problem set 10.2. Given mu, consider the minimization problem. Minimum sigma x square subject to x up to xn equals to 1 and erx greater than or equal mu. Show the following. 1. If mu is greater than the expected return on the minimum variance portfolio, x minimum, then the solution to problem is the portfolio x star of mu equals to g plus h mu, where g equals to 1 by t b w e minus a w m and h equals to 1 by d b w e minus a w m. Number two, if mu is not greater than the expected return on the minimum variance portfolio x minimum, then portfolio x minimum is the solution to M. B show that G is the normalized portfolio and H is a self-financing portfolio. Number C, compute the variance of the return on the optimal portfolio in problem M. 2. Given mu, consider the minimization problem. Minimum sigma x square subject to x up to xn equals to 1 and erx greater than or equal mu. Show the following. 1. If mu is greater than the expected return on the minimum variance portfolio x minimum, then the solution to problem is the portfolio x star of mu equals to g plus h mu, where g equals to 1 by t b w e minus a w m and h equals to 1 by d b w e minus a w m. Number two, if mu is not greater than the expected return on the minimum variance portfolio x minimum, then portfolio x minimum is the solution to M. B show that G is the normalized portfolio and H is a self-financing portfolio. Number C, compute the variance of the return on the optimal portfolio in problem M. In this slide, solution of A for each tau greater than or equal 0, let x tau star denote the solution to the Markovitch optimization problem. Maximum tau er x minus variance rx subject to xc equals to 1. If tau equals to 0, then this problem reduced to minimum variance rx subject to xc equals to 1. The solution to mu no, m naught is the minimum variance portfolio x minimum equals to x naught star, that m naught star denote its expected return. We have shown in chapter 3 that the expected return uh, m tau star equals to er x tau star on the portfolio x tau star is given by er x tau star equals to a by c plus tau divided by 2d divided by c, where tau greater than or equal 0. Substitute tau equals to 0 into the formula, we can get m naught star equals to er x naught star equals to a by c. Consider two cases. 1 equals to 1 is mu greater than m naught star and mu less than or equal m naught star. In the latter case, the portfolio x minimum satisfied constraint because the expected return m naught star on this portfolio is not less than mu. Therefore, this portfolio minimizing the variance BRRX among all normalized portfolio x is the solution to problem. Thus, if mu less than or equal mu naught star, then the constraint ERX greater than or equal mu in the optimization problem is not binding. Let us now assume that mu greater than uh, m naught star, case 1, since m naught star equals to a by c and mu greater than a by c, there is strictly positive number tau such that tau equals to a by c. A by c tau d divided by 2 by c. Suppose the contrary, there is a normalized portfolio X with ERX greater than or equal mu and variance Rx less than variance R x tau star, but mu equals to er x tau star by virtue of the definition of tau and by virtue of formula 10.9 for the expected return on the portfolio x tau star. Consequently, erx greater than or equal erx tau star and variance rx less than variance rx tau star. This implies tau erx minus variance Rx greater than tau erx tau star minus variance Rx tau star, which means that X tau star is not a solution to the optimization problem, a contradiction. To complete the portfolio X star mu solving the optimization problem, in the case 1, it remains to express tau through mu by using formula 10.11 and substitute this value of tau into the expressions for X tau star. X tau star equals to X minimum plus tau z star divided by 2 equals to w divided by c plus tau divided by 2 into wm minus a by c we. See the theorem 3.1, tau divided by 2 equals to c divided by d, tau into mu minus a by c equals to c mu divided by d minus a by d. By substituting this value of tau by 2 into 10.12, we get x star mu equals to x tau star equals to w divided by c plus c mu divided by d minus a divided by d into Wm minus A by C We. We divided by C minus A by D into Wm minus A by C We plus mu C by D Wm minus A by C We to We divided by C minus A by D into Wm minus A by C We equals to minus A by D Wm plus D plus A squared divided by dc We equals to minus A by D Wm plus B by D We equals to Z. Recall that D equals to BC minus A square and expression 10.14 can be written as mu C by D Wm minus A by C We equals to mu A by D into C Wm minus A We equals to mu H. This proves formula 10.p. Let us show that G is a normalized portfolio and H is a self-financing portfolio. This follows from the computations. EG equals to 1 by D B into EWE minus uh, A into EWM equals to 1 by D BC square BC minus A square equals to 1 and EH equals to 1 by D into C uh, into EWM minus A of EWE equals to 1 by D CA minus AC equals to 0. Recall that A equals to EWM B equals to MWM, C equals to EWE, D equals to BC minus SS. In this slide, we can see the solution of question C. To compute the variance of the return on the optimization portfolio in problem, we use the formula obtained in chapter 4. E R x tau star equals to A by C plus tau D divided by 2C. Um, and variance R x tau star equals to 1 by C plus tau square D divided by 4C. If mu less than or equal m not star, then as has been proved, the solution to m mu is the minimum variance portfolio x minimum equals to x mu star. The variance of the return on this portfolio is equals to 1 by c, that mu greater than m not star, then x star of mu equals to x tau star where mu equals to a by c plus tau tau d divided by 2c. Therefore tau by 2 equals to c by d mu minus a by d. We have already used this equality, and so variance Rx of mu equals to variance Rx tau star equals to 1 by c uh, plus d by c by d mu minus a by d all square uh, d by c. To simplify the latter expression, we write 1 by d c mu square minus 2a mu plus d plus a square divided by 2 equals to 1 by d c into c mu square minus 2a mu plus b. Thus, if mu greater than m naught star, the answer is variance r x star of mu equals to 1 by d c mu square minus 2 a mu plus b. Thank you so much for staying with me. See you again in the future.